The next section for this unit is dealing with electron configurations. It was mentioned in the video that we saw in class, and let's look at it at a more simplified way. You will also be doing an activity on this using a bunk bed slash boarding house scenario to help you understand how we fill and how we count electrons. So electron configurations is another way of saying arrangement. So we're looking for a seating chart for where we're placing electrons around the nucleus of the atom. So the arrangement of the electrons around the nucleus. All neutral atoms have the same number of protons and electrons for a particular element. So carbon should have 6 electrons and uranium should have 92 electrons when they are neutral. So we need to try and place these guys on where they're at. Currently we know about the Bohr model. So let's look at how we arrange them. Electrons are arranged in shells, and the shell is the distance from the nucleus where the electron may reside. Once again, we're talking about Bohr models when we use the term shells. Shells also represent energy levels, so that's a bit of a review. And the lower shells represent lower energy levels. Higher shells are higher energy levels. The electrons are attracted to the positive nucleus. Keep in mind, opposites do attract, so they cluster as close to the nucleus as possible. So what happens when they're filling their seating charts or their shells, they fill the lowest shells first, and they like to have the lowest amount of energy as possible. If shells represent energy levels, then orbitals represent the probable position of the electron in the energy level. So we're looking at the probable location or the most likely volume that it will take place in. So where the electron is going to be. So shells are just like those little rings. Orbitals are a volume of space. So orbitals, we also call them subshells or sublevels. In some textbooks they say sublevels, at least the chemistry book does, and then I think our textbook does refer to them as subshells. There can be multiple orbitals per shell, so there's more than one picture for each orbital within an energy level. Now remember we talked about Schrodinger came up with an equation for the atom to help locate where electrons are. So that's what we're talking about now, are those orbitals or those configurations that Schrodinger calculated, that volume of space. So each orbital can only hold 2 electrons maximum. Where the electron is located is in the orbital, and it's determined by the pulling of the protons and the pushing by other electrons. So let's look at the first energy level. There's only one orbital. This orbital is called the s orbital. And all energy levels have an s orbital. So when we drew our periodic table, we kept saying about the s section, the s section. Notice every energy level has elements in that section. There's the section on the far left. So the first energy level looks like a sphere. It is the closest to the nucleus. It has 2 electrons. They push on each other as far as they can be, is about 180 degrees. So they do push on each other, and they can be anywhere in that ball except in the very, very center, which is the nucleus. The first electron level can only hold 2 electrons. So when we look at the S section of the periodic table, we notice that it is only 2 columns wide. The third energy level, the second energy level, which is where the third electron starts to place. So now we're in energy level 2, but we are still in the S section. So when the first energy level has 2 electrons, they completely fill that space. We need to move on. So a new electron will be pushed away and move to the higher second energy level. So now we are in the second row of the periodic table, and that third electron is located in the S section. So the second energy level has 1 s orbital and 3 p orbitals. So the p section is on the further right. Each p orbital can also hold 2 electrons, just like the s orbital. So we get the total of electrons of 6. So the second energy level has a total of 8 electrons. So we have 2 coming from the s, and then we have 6 electrons on the right, so in that p section, and there are 3 different p orbitals, each holding 2 electrons. One of the p orbitals is called p sub x, so it looks like barbells or propellers. Notice that they're not really touching in the center. That's where the nucleus is, so we have these volumes of space on the x-axis. We also have p sub y, so they're on the other axes. And then we also have p sub z orbitals where they're going up and down. So we have 3 different axes in a 3-dimensional diagram, and we have dumbbells that can be on each axis. Those electrons that are located in the p section can be in any one of these dumbbells. These are the possible spaces that they could be in. And once again, Schrodinger's equation, when he plotted all of the information on a graph, he got these diagrams. After that, we go to the third energy level. The third energy level has 1 s orbital, 3 p orbitals. So if you look at energy level 3, we colored that in. We go across, but we did not get to the d orbitals. We had that colored in for periods as just being a 4. So we are changing our diagram for energy levels when we're doing electron configuration. So the large periodic table on the front of the classroom is colored based on the energy levels and orbitals. So the third energy level has a total of 18 electrons, 2 from the s orbital, 6 from the p orbital, and 10 from the d orbital. Keep in mind, for every orbital there are 2 electrons, so we can count those out. Energy levels 4 through 7, we add another type of orbital called the f orbital, which is that bottom part of the periodic table, our little island from Seaborg. There are 7 orbitals, giving us 14 electrons at each level, so there are 14 blocks wide in that section of the periodic table. That allows us to place all the electrons that we need for any element. Keep in mind, we can keep building this as much as we want to, but we don't have elements or electrons to support all those new positions. So there are diagrams for all of these, and you can graph them all with Schrodinger's equation. However, we're limited on what elements we have, so there's no need to go beyond that. So in your notes, I did have this diagram. Remember I said helium, we definitely want to push over to the S section, so you can draw him in there if you want, or make sure you have a little line like the diagram has. And it is surrounded in orange. And then we have the P block, or the P section, over on the right side. So we have those 6 wide. And then we have the D section in the middle. Those are our Roman numerals with the B's. So the representative elements are the ones in the A's in columns 1, 2, and then columns 13 through 18, except helium. As well as our B, Roman numeral B's, are our transition metals, and they are in the D block. And then we have the lanthanides and actinides in this periodic table, showing it a little bit different, but we have that F section. I told you that some periodic tables show cerium and thorium as the beginning versus lanthanum and actinum. So just use the periodic table as that guideline that that bottom section is the F block.